Welcome everyone to the Experience AI webinars. I'm Mac, a content creator for Experience AI.
Hello everyone, I'm Veronica. I'm a research scientist and I'm responsible for the explanations used in the Experience AI unit.
Happy New Year, Veronica. I was wondering if you had any resolutions for this year.
Happy New Year, Mac. Yes, I do. I'm planning to read a little bit more. I read a lot of research papers and I quite like to read a bit more fiction this year. So that's my resolution. How about you?
That's a really good one. I also love reading, so I think, yeah, doing more of it's always a good thing. Mine is actually stretching. So I work from home quite a lot, and sitting in my chair all day, I think, has led me to be quite inflexible. So I'm going to try and do some more yoga this year to sort that out a little bit.
Nice. How about the world of AI? What makes you excited for the year 2024?
Well, it's hard to make predictions. It all moves so fast. But I think for me, there's still some really big unanswered questions around privacy, copyright, and transparency that I hope we make some headway on as a society in 2024. I think they are really big and they require us to have kind of really serious conversations. But I'm looking forward to seeing how we work that out. How about you? Well, what are you looking forward to in AI in 2024?
Definitely. I think, what you said. I mean, it's the biggest election year. I think there'll be like the biggest number of elections happening across the world this year than any others. And I think AI will definitely have an impact to some extent on those. So I'm really interested to see how that unfolds, what the repercussions are, how the world will react. But also, I think there's some really interesting developments in the world of science and medicine that I think AI again has a really big impact on. So I'm really excited to see what happens there.
Yeah, I think it will be exciting to see the sort of advancements and also, what's going on with the elections and everything and how AI will play a role. So yeah, let's keep an eye on it, hey? And I think, to be honest, the subject of today's webinar will have an impact on all those things that we just spoke about, because today we're going to look at machine learning models and machine learning engines.
Definitely, yeah, models and engines. Machine learning models certainly are at the core of the Experience AI lessons. And I wonder, Mac, if you can explain a little bit of where machine learning fits in the overall framework that we're using in the lessons.
Happily, yeah. So for the lessons, when we were designing them and writing them, we really tried to use the CME model, which has different layers that allows you to kind of split them up. And there's a really clear place where I think models fit into that. So let's bring those up on screen, Veronica. And if you kind of talk us through the layers that are on there, I know that you have a lot to do with the sort of definitions of this.
For sure, yeah. So the way we think about AI, the way we break things down a little bit, the foundation is we think of these four levels. First is the social and ethical level, the impact that the AI has on society, on the world, on the individuals. We have the application layer next, which are the individual tools that we use without potentially knowing so much about how they work, but that we use for different purposes. Further on from that, we have the model level at which we think about, where we discuss how models are trained, the data, how we collect and clean and use the data to train machine learning models. The fourth, we have the engine level, which concerns the specific algorithms. So, for example, decision trees or neural networks, which are used in combination with the data to create these machine learning models.
Exactly, yeah. And you can see the sort of technicality increasing as we go down those levels, right? You're more in the sort of nitty-gritty of it as you get down. So today we're going to focus on those bottom two levels, right? So models and engines. We're going to explore what a model is, how machine learning is used to create them, and in the end, we're going to look at a specific example of a machine learning engine, decision trees. So some of the most kind of technically complex topics in the unit, but we're going to kind of open them up and talk a bit about them with you.
Definitely. And we also have a guest joining us to help us with that. And they're going to share their expertise and insights so we can put it in real world context a little bit better. Hi, Thomas.
Hey, Thomas.
Hello.
Thank you so much for joining us. Just a reminder for everybody watching at home, if you have any questions during the webinar, you can post them in the comments, or you can follow the link on screen right now, submit them, and we will try to get to most of them at the end of the webinar.
Thomas, very nice to see you. Thomas works at Google DeepMind, and we're very excited to have you here on the webinar today. Can you tell us a little bit about yourself and the work that you do?
Yeah, sure. Yeah, so I'm a research engineer at Google DeepMind, which means I build machine learning models for a living. And yeah, I've been doing this for almost 6 years now. And before that, I worked in particle physics, also mostly doing machine learning. And yeah, so during my career, I worked on a lot of different topics. So first, during my PhD in particle physics, using actually boosted decision trees to reconstruct particle decays. And then later, when I joined DeepMind, I worked with the science team on things like using graph neural networks to predict physical properties of materials, or use Monte Carlo tree search-based methods for mathematics. And then in the past years, I focused more on like hierarchical reinforcement learning in 3D simulations and on embodiment of large language models.
Amazing. Well, I'm really excited to discuss machine learning models and engines and everything with you. I think you'll have lots of expertise to share with the educators that are watching.
Yeah, so it would be good to start the discussion today looking at models, machine learning models, and we hear the phrase and the concept of machine learning models a lot. But Thomas, I want, if possible, for you to explain what is a machine learning model and what does that mean to you?
Yeah, sure. So a model is usually, we mean by model an approximate and often like simplified representation of a system that allows us to predict the behavior of it. And might be best explained with a few examples. So as a physicist, right, physicists use mathematical models. For instance, Newton's gravitational law can be used to model the movement of Earth around the sun. And that model is not 100% accurate, as we know since Einstein, but it's nevertheless a very useful model to predict the movement. And another example could be like weather prediction, where meteorologists use computational models to simulate the atmosphere and the oceans in order then to predict the weather for the upcoming days. And again, that model does not reflect reality 100%. It's not exactly accurate, but it describes the system well enough to allow us to make useful predictions.
Awesome. So when you say, a representation of a system, the system you mean is like a real world context or some environment in which you want a model to either recreate or maybe operate. Awesome. So if a model is that representation of a system or a context, how does like machine learning play into it? So what makes it a machine learning model rather than like a mathematical model, for example?
Yeah, so machine learning is really like a collection of different methods that allow us to build models from data. And that's often very useful when we try to build a model of a very complex system, where there's no easy mathematical formula that anyone could write down. So just coming back to these previous examples, the Newton's gravitational law is a fixed, easy mathematical equation. And that describes the solar system, and there's no need for machine learning at that particular point to describe the system. But in contrast, if you look at weather systems, it's much, much more complex. And hence there it's convenient to use machine learning and the tools of machine learning to build weather prediction systems based on historical weather records. There's some recent work from Google DeepMind, for example, is GraphCast, which is state-of-the-art weather prediction system built on machine learning methods.
Amazing. Oh, cool.
And how far in the future does it go, Thomas?
So that focus, I think, up to like 10 days.
Oh, pretty good.
In principle, right, you can unroll this for as long as you want, but at a certain point, the model is no longer useful because it's not that accurate. You can predict a year, but it will be random.
Right. So the 10 days are what we can predict sort of accurately enough to be useful, but everything after that might not be useful or accurate enough to
Yeah, a model is always has always a context of a domain where it's valid to accurately describes the reality.
Right. Right. So machine learning models are representations of real-world contexts, problems that have been created using a data-driven approach.
Exactly. So I guess the next logical question is, what is machine learning? And I think you already gave a little bit of an answer to that, Thomas. But I think one of the things that I've noticed when talking to people, one of the things we try to approach in the lessons is the difference between AI and machine learning. Sort of in media, we often hear these two terms sort of used quite interchangeably. And so I think one of the important concepts we try to get across to the young people in the lessons is how to differentiate between the two. So yeah, what would you say are the sort of key differences between AI and machine learning, and what do young people need to know to be able to differentiate between the two?
Yeah, you're right. Those two terms, usually in particular outside of science, by journalists, politicians, they just use AI for everything now. AI really stands for artificial intelligence, and that's an idea that goes back a long time, where if intelligent beings like humans and animals can be described using mathematics and physics, then it should be possible to artificially build a machine that is intelligent, right? And that idea in itself doesn't prescribe how to build such a machine. It just says, oh, it should be possible. And then, for example, in the last century, people actually mostly focused on what is now called symbolic AI. And that was an attempt to create an AI with symbolic representation and logic rules, which are handcrafted. And people would just put in like, if I say this, the model should react like this. And they thought, if I just put enough rules in there, then at some point the model will be complex enough to mimic an intelligent system. And they had no machine learning back then. They neither had the data nor the compute. So that was the approach that they chose. But ultimately, that attempt kind of failed. And today, most researchers now use methods from machine learning to build AI systems or try to build AI systems. But it's really like, one is a system, an idea of an artificial intelligent artifact that you want to build. And the other is a tool set that you can use for AI, but there are many other things that you can do with it.
I see. So yeah, you could almost say that machine learning is a part of AI, but it's not the whole of these this attempt, this field of research. That's great.
Yeah, you can do AI without using machine learning. It probably won't get very far, but you could.
Yeah, that's true. Yeah, especially not. And now those techniques, I feel, have moved on to such a point where they are so useful that that's why they're getting so much attention nowadays, is because we've managed to make sort of quite big strides using machine learning techniques. I say we, but actually I mean you, Thomas, more so than me. I just teach people about it.
Yeah, thank you, Thomas. And so when creating the explanations for the Experience AI unit, we explain machine learning as a collection of approaches used to design and build artificial intelligence systems, amongst others, exactly like you said, Thomas. And machine learning, we talk about machine learning as learning by using examples in the form of data, instead of using step-by-step instructions, or instead of the rule-based systems that you described, Thomas.
Yeah, exactly. It's not just, machine learning isn't just one thing. There are loads of different, even within machine learning, right? Just like there are loads of techniques for AI within machine learning as well. There are lots of different techniques, lots of different approaches that you can use. In the unit, we cover 3 different types of machine learning. And I thought it would be useful to kind of go through them now and ask Thomas, if you wouldn't mind, we can ask you some questions about them, and hopefully your expertise can kind of illuminate these subjects. So, and for you watching at home, hopefully you can get some stuff to take with you into the classroom, some stories or some examples that you maybe haven't heard before.
Yeah, so let's start with supervised learning, because Mac, this one features in the lessons a lot. Can you describe it very simply?
Absolutely, yeah. So we focus on supervised learning quite a lot throughout the whole of the lessons after teaching about these 3 different types. So supervised learning uses large amounts of training data that has been labeled by people with the relevant output. The model is trained to produce the correct labels for the training data with the hope that it can accurately label brand new data when it's deployed.
Yeah, so I guess an example of supervised learning might be, for example, a machine learning model trained to recognize fruits and vegetables in images. And we might use lot and example images with fruits and vegetables in them to train a model. And it sounds simple enough, but what are the challenges with supervised learning, Thomas?
Yeah, so apart from training the model itself, of course, which is a challenge in itself, there are like two big challenges, I would say. So one is getting enough high quality data. So the quantity and quality of that data is really key for these machine learning models to work. And then there's a whole process of collecting that data, pre-processing it, cleaning it. And often that's like the majority of the work when it comes to build machine learning models. And then you build your model once you have that. And once you have the model, that's when the other big challenge comes. Now you have a model, but how do you know that this model is actually doing what you think it does? How do you know that the model provides accurate prediction in real-world applications? And there are like a lot of tragic failure cases in the past decades or so that you could look at. So where people build machine learning models, but it didn't put enough effort in evaluating them. And then, for instance, the models that are trained on data that contain biases, they can lead to machine learning models that then discriminate against, for example, minorities. And that is quite harmless in the example of the fruits and vegetables that you mentioned, right? So if a system fails to recognize apples, I guess that's probably okay. But if we're talking about a face recognition software that runs on your phone and then only recognizes, let's say, white faces, that's a serious problem. And so evaluating the systems and to make sure that they don't inherit the biases in the data and that they perform in real-world scenarios for real people that perform well, this is a huge challenge.
Thank you. Yeah, I think there's, the issue of sort of bias and ethics and stuff in machine learning is so important. So the next webinar is actually going to be entirely focused on that, just because we think it is so important to kind of cover. But yeah, thank you so much, Thomas. Next, I wanted to touch on unsupervised learning. So we have supervised learning and then another type, which is called unsupervised learning. So I wondered, Thomas, if you could kind of illuminate what the main difference is between that supervised and unsupervised learning.
Yeah, so supervised learning, as you already mentioned, right? So that requires data where you have a correct answer. And in the previous example, right, you have images of fruit and vegetables. And if we have a correct answer, that means that for each image, we know, okay, what fruit or what vegetable is it? And this concrete answer is called the label or the ground truth of the data. And then in unsupervised learning, we don't need such a label. For example, if you just have a bunch of images for fruit and vegetables, and I don't tell you which one is which, you could still sort them, for example, by color. And that would probably still give you some kind of good separation between like the more greenish vegetables and the more colorful fruits. But you use like just the structure of the data itself to do, for example, some clustering. And so you're completely guided just by the structure of the data itself without having to provide a concrete supervision signal in form of these correct answers and labels.
I see. Great. So yeah, like I think the example we use quite often in the lessons is a streaming service, for example, using unsupervised learning to group users in order to provide them with recommendations. So they know the viewing habits, and then perhaps they could group those by viewing habits, and then know if it works with one person in this group, it is likely to work with other groups.
That makes sense. So we've got supervised learning, unsupervised learning, and the third main type is reinforcement learning. And I know that you do a lot of work with reinforcement learning models at DeepMind, Thomas. So can you describe this approach?
In reinforcement learning, so there's this concept of an agent that interacts with an environment. And then typically that agent takes a trial and error approach to explore the environment and tries to optimize some kind of reward. And again, it's probably best to look at a concrete example. So if I have a vacuum robot to clean my flat, then that robot is the agent because it can take actions like moving left, right, or forward, and the environment would be my flat. And then I could manually program the robot with the correct movement pattern beforehand. But that would be pretty cumbersome to do that, and it would only work for my flat. And if I move, I have to redo this entire thing. So I can use reinforcement learning instead to take my robot and always reward the robot if it has a movement pattern that collects dust. And then the robot would start with some random movement. And whenever it collects some dust, then I can reinforce that behavior by giving a reward and basically adapt the system such that this movement pattern becomes more likely. And then over time, as I keep on rewarding the robot for collecting dust and making the behavior, the movement pattern that led to collecting dust more likely, over time, the robot would converge to like the optimal movement pattern that collects like the largest amount of dust in the shortest time. And this is then a very general approach where I only have to define this reward, where I say, okay, I want to maximize the amount of dust collected. And then the system in itself will go out and collect the necessary data via trial and error and optimize automatically the behavior to find the best movement pattern, or what we call a policy, that maximizes this reward that I define as a researcher.
That makes sense. So it sounds a bit like reinforcement learning applies well where you have almost like a game-like context where you can apply kind of maximize the winning the point. And
yeah, I think
yeah, go ahead, Mac.
No, you go, Veronica.
Well, I was just wondering where we can find this covered in the lessons, Mac.
So all of this is covered in lesson 2. So there's a great video where another DeepMinder, Ashley, goes through all 3 types of machine learning. There's some animations to kind of help bring those concepts to life. And then we follow it up with a bit of a low stakes quiz to recap the sort of important characteristics of each type.
Nice. Yes, that is a really, really good video. And I wonder if we can maybe have a go at some of the questions from the lesson, a bit of an opportunity for audience participation. So I'll show the statements on the slide, and in the chat, you can tell me what type of machine learning you think the statement refers to. So let's take the first example. So a machine learning model where the model learns by trial and error. So, and we have, as explained so far, we have the options of supervised learning, unsupervised learning, or reinforcement learning. Which type of learning do you think aligns best with learning by trial and error?
And you can put 1, 2, or 3 in the chat as well if that's a bit quicker. Yeah, still coming in. Which one could it be? Go on, Veronica. Let them know.
So this is reinforcement learning. You might have guessed, as Thomas explained really well, it keeps trying, and based on rewards or punishment, it adjusts its behavior to maximize its rewards. Shall we have a look at the next one?
Go for it.
So which type of machine learning is described based by saying grouping data that is similar? So again,
think back to the sort of explanations and what Thomas was saying. So which one would sort of use, go over the data and maybe group data together based on similar characteristics?
Nice.
Some stuff coming
we have
in.
a few. Yeah, responses. But yeah, that's right too. Unsupervised learning, that's the one. So groups data or clusters data based on similarities. And the last one, which type of learning, machine learning, is best described by saying that the training requires example data. We gave a couple of examples around this.
Exactly.
Yeah, exactly. Yeah, people are
coming in.
It is the last one remaining, supervised learning. So supervised learning, where we absolutely need example data with that ground truth to be able to predict on new data.
Great. Well, Thomas, thank you so much for offering your expertise so far. We're going to take you off screen for a minute, but don't go too far because we're going to bring you back at the end for a bit of a Q&A. But yeah, it's a chance for you to have a bit of a drink and stretch your legs if you want to. But yeah, don't go too far. We'll bring you back. Thank you.
Okay, next, Matt, I think it would be really useful to look at a specific example of machine learning, a real problem it can help solve, and maybe we should have a look at an example of a model and how we build it.
Exactly. So as we said, sort of in the lessons, we have a real focus on supervised learning because, picking one of the types so that we can breathe some understanding in it. So, and the type of problem that is really, really good for supervised learning to help solve is classification. So what are the explanations that we give as part of Experience AI have to say about classification?
So explaining classification as the task of assigning things into predefined groups called classes. And a classification model predicts one or more class labels.
Great. So in the unit, we use the examples of labeling fruit based on images, which is very similar to the example we used earlier. So there's using supervised learning, a classification model would be trained with pre-labeled images, loads of pre-labeled images, like Thomas was saying, the quantity that's needed and also the quality to get a good model. So loads and loads with, each of those images being labeled with the correct fruit. And then after training, we'd hope that the model would be able to correctly label a new image of a fruit that we showed it. So it would be able to say whether it was a banana, an apple, grapes, or anything that it had seen in the training data.
Exactly, yeah. And another example of classification is sentiment analysis. So let's say you have a product that you're trying to sell and you might want to learn how your customers are responding to it, whether they're responding positively or negatively. You could use supervised learning to label reviews. One review is positive, one review is negative, and be able to understand better how people feel about your product based on this sentiment analysis.
Exactly. So the training data in this case would be the text from the reviews, and the classes the model could label with would be positive and negative. You would train the model to label new reviews as they come in. So this is a really useful tool in getting a high-level overview of how your product is received without having to start dig in to every single review, right? So you would label some early reviews, and then the machine learning model hopefully could label ones as they came in.
Yeah, exactly, and trigger you to only have a look at the negative ones, for example, or something like that. That's right. Yeah, and because classification is not just about applying a single label, a model might be able to apply many labels to exactly the same image.
Exactly. Data doesn't have to have just one label or just one class. So in computer vision, which is another example that we use in the lessons, a model is trained to identify a range of different objects in an image. So in this image here, you can see the example. There are lots of different classes. So, you have person, dog, shoe, bicycle, and each of them will have what is a confidence score, which is how the accuracy the model thinks that label is approved, or the model has assigned to that prediction.
Yeah. So there are these kind of I guess category of problems where classification problems that supervised learning can be really helpful for. So I think next it will be really useful to see how a classification model might be trained with concrete example data.
Exactly. So in lesson 4 of the unit, we do this exact thing using a type of machine learning engine called a decision tree. Decision trees are a really good example of a type of, so this is a type of machine learning engine that we spoke about at the beginning, right? This is a specific algorithm that is used to create a model that forms the basis of it. So decision trees, and the reason we chose that for the unit is because they have a really visual element, right? So when you're showing this to learners, they can see something, but also they have a relatively straightforward creation process that for someone who's just beginning to look at these sorts of things is a bit simpler to get your head around and also to play around with and kind of garner some understanding.
Definitely. So you can think of a decision tree like a flow chart. They're made up of nodes and connections between these nodes. And there are two types of nodes, decision nodes and leaf nodes, as you can see in the diagram.
Exactly. So the leaf nodes are usually towards the bottom of the decision tree, and each leaf node would represent a single class. So the way you use a decision tree in practice is you take a piece of data and then you work from the top all the way until you reach a leaf, and that would provide the prediction of the label for you. So a leaf is a single class.
Exactly. And the decision nodes help you direct you through the tree so you can navigate the tree. They contain the decision nodes, they're called decision nodes because they contain a condition, a test that you apply to your data to make a decision. So the result of that test will be the true or false, the decision of true or false. And this controls the direction, the way in which you navigate through the tree towards a leaf node.
So for this webinar, we are interested in how a decision tree is made. In lesson 4, we have an activity that uses star cards. The context is helping classify new stars that are found by the James Webb Telescope, a project that space agencies around the world have contributed to in order to take long-range photos from space. Stars themselves can be classified into things like white dwarf, main sequence, and hypergiant. So like our sun, for example, is a main sequence star.
Yeah, so your learners get to create their own decision tree with training data found on star cards. The star cards on them have information, features like temperature of the star, radius, brightness, or color of the star. And they're called features, bits of data that describe each star. And the bits of data will be what your conditions will be around, so they will test to classify the stars.
Exactly. So we call these features, right? When we're trying to make a decision tree, yeah, the bits of data like temperature, radius, and brightness are each called a feature. So here is, I'm going to model one of the sort of activities we have in lesson 4 for your learners to get to grips with decision trees. So the first thing we need if we're going to create a machine learning model is training data. So here I have our training data. Now we're going to do this by hand. So we've got 6 pieces of training data. Like we said before, in the real world, in what Thomas does at DeepMind, you would have obviously many more, and maybe 1 million times more pieces of data. But in this case, we're just going to use 6 pieces of training data. You can see here, this is the star cards we were talking about earlier. So each of these has the data about a single star that has been spotted by the James Webb Telescope. And we have 3 different classes. So we have red dwarf, we have main sequence, and we have supergiant. So when we're creating a decision tree, what we're trying to do is split the data using those conditions in such a way that we get closer to classifying a star. So the first thing to do is to choose one of our features and then arrange our training data in order from lowest to highest of that feature. So in this case, I'm going to start with temperature. Right, that is it's the first one on the list. When these models are created, there may be many trial and errors of trying different features and seeing which one gives the best split, but I'm going to go for temperature this time. So I'm just going to drag these around into order. So I think the very first one is this red dwarf here. So we'll put that over there. Then, dragged just the card, not the sequence. So drag that one there. Then I think it's the next red dwarf.
Yeah.
Then this one.
Mm-hmm.
And this one next.
Mm-hmm.
Oh yeah, that one's much warmer, isn't it?
Yes, it is.
So when you are doing this in your classroom or wherever you kind of use these lessons, you might get asked about these features. So temperature is obviously in degrees, but both radius and brightness are relative in the data set. So this means that the radius is 97 times larger than our sun, and this is 6.63 times smaller. Sorry, less bright than our sun. So those numbers are a little bit weird. So we've arranged these now by temperature. So this has worked out very well for me. It's almost as if I planned it, but you can see that these have been sorted now into classes, right? So we have red dwarf, main sequence, and supergiant. So now we need to decide where we would like to split this data. So we could say split it in the middle, right? And get that on one side and that on the other, right? And our condition, we would write our condition as such that all the stars on this side would fall on the true branch and these would fall on the false branch. But this isn't a very good split, and it isn't going to get us any closer to making a prediction. And the reason is that we still have two classes on either side. We would need another split on both sides in order to get to a single class in that leaf like we described. So instead, we want to pick a split where we are left with a single class on one side and then the other side maybe could have another split in order to take it apart. So in this case, what I'd suggest is, and you can get your learners to kind of suggest where they would split it, but I'm going to suggest that we split it in between the red dwarf and the main sequence. So what we do is we're going to formulate our condition and we're going to move the red dwarfs up. So you can see actually this is an example of the sheet I already did. So this is actually already done. Mm-hmm. And then we've got our first condition, right? So our test is if temperature is less than or equal to 3,467, we're going to go on one side, and then on the other side, which is the false branch, we have these 4 star cards that are left. And that number is found by taking the average of the 2 stars either side, right? So we've added these 2 temperatures together and then divided by 2 to get that number there.
Nice.
Okay. So now we've correctly classified, or we've correctly arrived at a leaf for red dwarf, right? We're only creating the model at this point, so we can't say we've classified, but what we've done is we've isolated red dwarf on this side. So next we're going to create the second split. So the second split, the only advice we give in the lesson is don't use the same feature again. This is because you don't want to split it by temperature and then split it by temperature again, because you could have a more complex sort of condition at the top. So instead, we decided to use a different feature this time. So I'm going to go for radius, I think, because they're already sort of sorted. Oh, slightly. I just need to move these 2 around. So we'll go for radius this time. And again, we don't want to split it with 1 on one side and two classes on the other. Instead, we want to try to find a way to cleanly split it in the middle. So instead, we're going to go somewhere around here, split those up. So then we'll end up with a main sequence on this side, and supergiant on this side. Now, again, this is a simplified example with only 6 items of data, and we've made it so that your learners, no matter what age they are, can kind of do the sorting and do the splitting without too much of a headache. But just imagine this same process, but done with 241 stars and all 15 features that all are very complicated. And that is why we get computers and machine learning to help us do this for really complex data sets. So we can actually see the answer. So if we bring the slides back, if possible. Yeah, great.
So now we have a tree that can classify stars and are based on temperature, radius, and other features. Nice. Thanks, Max. That's a really good demo. So once the learners are comfortable with this process and you go through it with them once, you can give them, and we have this in the lessons, You can give them new training data and ask them to make a whole new tree where the features have different values. So in the end, you end up with two completely different models. And this is one implication of using a data-driven approach, where different data leads to a different model. So depending on what data from which stars you've got in your data set, you might end up with a different model.
Exactly. And this just goes to show you another thing that sort of Thomas was saying earlier, right? Is about the quality of that data, because you will end up with very different, decision trees or, these machine learning models that might not account for things they haven't seen in their training data. So yeah, it's a really important point, and I think it's good that the learners get to see that in action, two different results. So yeah, like I said, we've limited the number of stars here. So there could be something that could be done by hand and could be taught to sort of many it could be taught to many people at once. So this is a simplified example, but the idea is that they can see how them acting as the algorithm, as the engine that is creating the model, has they can see how that data-driven approach changes, but also remember to impress upon them the need for machine learning to help with the scale, right? The scale of millions of pieces of data, loads of features, and trying to compare them all and choose the best one.
Right, potentially many classes. That's right. And decision trees are just one type of machine learning that works well for solving some problems. Decision trees are great, also do help in teaching a type of engine to help understand some of the underlying concepts behind supervised learning and classification. It's quite visual. There are many other types of engines, including neural networks, that are potentially better suited for other type of problems. So, for example, if we only had image data, it might be more appropriate to use something like neural networks. But I know Thomas has experience of different models, and so it'd be good to bring him back in and talk about. Hi, Thomas.
Hello again, Thomas. Thank you for not running away too far. We really appreciate it. I think you're on mute before you talk, just as a point. So I guess the first thing I want to ask is, do you know of anywhere where this type of machine learning engine, decision trees, is used in the real, in the real world in the AI industry?
Well, decision trees are actually quite prominent, in particular in, I would say, the last 2 decades, because they do have some advantages over neural networks, so that they are easy to train and often require less data compared to neural networks. Of course, nowadays we have a lot of data, that's why we move further to them, and we have the resources to invest like experts in training these things. But in particular, for beginners or people who are not that deep into machine learning, decision trees are like a really robust thing to just start with. And a good example is probably the Higgs discovery from 2012, right? That was boosted decision trees. So in physics, we've been using them a lot for these kind of things. And another advantage is that they're also very interpretable, which is what we would just see. And that means that in a lot of applications, it is actually necessary to be able to tell why a model made a certain output. And in all of these like examples where it's important for like in industry to have an interpretation of why a model made a certain decision, that's where boosted decision trees or decision trees are really, really useful. Another example that I know personally, what people done a lot is, for example, in logistics. So if you want to predict, like for supermarkets, how much fresh fruit you want to have stocked, this is often also done just with decision trees. Basically all over the place.
We talk about that in the unit a little bit, the sort of element of explainability that is really good with decision trees, right? You can follow that output through. So thank you.
I have another question for you, Thomas. Do you think that the unsupervised learning model are a lot less would you say that they're a lot less accurate than supervised learning models?
No, not necessarily. So typically, it depends on the actual use case. But yes, if I have a supervision signal, if I have the same amount of data, so if I take my data set and I just take away the labels, then sure, the supervised learning method making use of the labels will be better than if I use the same data and try an unsupervised method. So that's probably true, but there is a lot more unsupervised data around that you can easily get. It's way harder to get these labels. So typically you have a lot more unsupervised data if you go with an unsupervised approach, and therefore, depending on how much more data, you might get a better model out. But that then really depends on the actual application.
That makes a lot of sense.
Just a quick reminder for those of you watching, if you have any questions that you'd like Thomas to answer, make sure to put them in the comments or use the form, which is just shown up on screen now. Thank you, people in the background, for doing that. So I had another sort of, going back to the decision trees and that example of an engine that we used. I wondered what, that process of seeing a decision tree created, even if it's simple, what do you think that can teach young people about other engines, for example, say neural networks, and how those are trained and created?
So there's of course the aspect of, and if I train a decision tree, like in a real world example, then a lot of the steps that we already discussed previously are identical to the neural network case, right? I have to get my data. I have to decide on my what paradigm I use, like supervised or unsupervised or reinforcement learning. I have to evaluate my model. So all of these complexities, they are completely agnostic of what kind of model I use underneath. So all of that, these concepts will translate. And then more like statistical knowledge about, I guess you will go into this in your courses on like overfitting, underfitting in models, the bias variance trade-off. All of that is also independent of the actual method used. So I think it's probably most of the knowledge you can transfer between the different models.
Great. I really thank you for saying. I think, like, as somebody who maybe is inexperienced with these things, you see a decision tree that seems quite understandable when you look at it, and you might think, oh, there's no way there's anything like compared to, neural networks I've heard about, or I might have seen vague graph drawings of that seem really complicated in the world. But it's really reassuring to know that through these, simplistic examples, we can actually, get some high level understanding of how more, what would traditionally be seen as more complex models are created.
Definitely. And then another and potentially last question. Why is reinforcement learning, the type of machine learning called reinforcement learning, so popular in especially modern AI development?
Well, yeah, that's an interesting question. So it was quite popular in the past decade, and that has been fueled by all these breakthroughs in games like Go and StarCraft, and DeepMind did a lot of work there. Yeah. But today, actually, we had a bit of a paradigm shift in like let's say the last 3 years.
Okay, do tell.
Where the field converged more to actually use all 3 methods. So the latest trend in AI is really using these large language models, which people probably know from Bard, from Google, or ChatGPT. And those large language models, they are trained with all 3 paradigms. They first use like unsupervised learning on a large text corpus just from the internet. And then you use supervised learning on top of that. So you first do unsupervised learning with your model, and then you get a smaller, curated, high-quality question-answer data set where you fine-tune this model now with a supervised approach, where you say, here's a question and the desired answer. And then finally, people do reinforcement learning with humans in the loop, where humans interact with the model and provide feedback, which is then the reward of more of this behavior, less of this behavior, where you then align them to the needs of humans. And this then goes into like questions on safety and factualness and and these kinds of things. So all three basically are fueling the current large language model trend that is, I think, the dominant paradigm currently in AI.
Yeah, definitely. I think the large language models has taken over quite a lot of the conversation. I think shortly behind, followed by sort of image generation, which is the two that you seem to hear the most about in the world. So I think this is our last question. So this one came in from the chat. I think it was from the same person that asked the question about which is more accurate, supervised or unsupervised. So somebody is constructing a sort of battle royale of all three types. So they wondered, if you were to compare efficiency or accuracy, would reinforcement learning be the most accurate, or is it just that they're different approaches?
Well, they're different scenarios, right? So technically speaking, reinforcement learning solves a sequential decision-making process. So the reinforcement learning is really, I have this environment where I take these actions and then the environment changes, like my robot moves through, which is in a sense a different scenario than me classifying things. Right? Classification, like supervised learning, and if I want to learn a behavior, I have to somehow use some reinforcement learning method there to actually get out a behavior as a result. But you can roughly compare. Sometimes it is possible to compare the approaches, and then typically it's like if you have the same amount of data, it's like you have your supervised learning, and then as soon as you go to reinforcement learning, you need like at least 10x more data or 10x more interactions with the environment. It's like a rule of thumb to get like the same result. But there is also an advantage to reinforcement learning, which is with the supervised learning, I need the answers from an expert, right? Let's say I want to learn chess. It's a good example. I can learn this supervised by having an expert tell me what is the best move in each situation. But then that model can never get better than that expert, right? Because it just mimics the expert answers. Whereas the reinforcement learning approach, although it will require more data and more games, actually has an unbounded, or probably unbounded ELO score in the end. So as long as you train, it gets better and better and better because it creates its own data and finds ways to optimize the policy further and further. And that's why things like AlphaGo and AlphaZero, like these engines that play chess and go at a superhuman level, are possible. They aren't possible with just supervised learning because we won't have the correct answers. What is the best chess move? But with reinforcement learning, adding more compute, we can actually go beyond humans.
Amazing. That's such a good example. Thank you so much for that, Thomas.
Such a good way of looking at things. And you often think of supervised data with like ground truth as like the ultimate because you have what you are looking for in the answer, but you don't often think of that as limited. You think like that's what we're aiming for, and actually to think that there are possible limitations, and you can go even further. That's such a good way of looking at it. Thank you, Thomas.
So just maybe one more word for the most interesting questions in science and for humanity. We don't know the answers yet.
Right.
So that's why a lot of people conceptually like reinforcement learning for just this philosophical viewpoint.
Definitely. Yeah. Oh, really sadly, that brings us to the end of our webinar and our deep dive into machine learning models and engines. Thank you so much, Thomas, for joining us in this discussion. It was really interesting to hear your thoughts and answers, and I could have kept going with questions forever. And I'm sure that the educators that are participating here and they will watch later, and the young people taught by them will definitely benefit from this. Mark, do you have any last takeaways from this webinar?
apart from saying thank you again to Thomas, really appreciate you giving such thoughtful answers and some really great examples. So I think that was super duper valuable. But just a sort of reminder for the educators at home that, you know, we said at the top of the webinar, but it's worth repeating that the things that we've looked at today are some of the most complicated topics in the unit. But I think the way the lessons break them down and use abstracted, simplified examples like the decision tree that you saw to make them more relatable and understandable for your young people. It's just, I think it was a really good choice on our part, and I think it's just the best way to tackle them. My encouragement to you is try not to worry about being a machine learning expert and focus on what the examples in the lessons are aiming at, which is a high level grasp of the underlying technologies involved in modern AI. Like Thomas said, it might seem a simple example, that decision tree, but if they can understand that process and see how that trained data results in different models and how those, you know, conditions are made, they will be learning something at a high level about all different machine learning engines.
Couldn't agree more, Mac. And beyond the unit lessons, we do want to draw your attention to the AI challenge, which is now open. It's a free challenge that encourages young people to create with artificial intelligence and machine learning. You can visit the link at the bottom of the screen to access free resources and further details on the challenge. And it's available to anyone from any country to use and to download and use. Although challenge submissions are only currently available to the UK residents in this pilot phase, and they're only open until the 24th of May. So if you are interested, do be aware. But anyone in the world can still download and use the resources wherever you are in the world.
Yeah, really excited to see the submissions and people get involved with those resources. I think they're really exciting. So yeah, looking forward to that. But on that note, our next and final webinar is on the 7th of February, where Veronica will be back with Tessie to discuss the role of bias and ethics in AI. We are looking forward to seeing you all then. I hope you have a wonderful rest of your Wednesday and a great week. We'll see you later.
Thank you. Thanks,
Bye.
everyone. Bye-bye.
Bye.
Bye. Thank you again.